Welcome back to the Science Hub SKB with Miss B. In part 2, the following objectives will be covered. What is an echo? Noise versus musical notes, and the human ear. What is an echo? Oh. An echo is a reflected sound that is heard after the original sound has been produced. An echo is a reflection of sound. Sound waves are reflected well from hard, flat surfaces such as walls or cliffs and obey the same laws of reflection as light. The laws of reflection state that 1. The angle of incidence is equal to the angle of reflection, and 2. The incident ray, the normal, and the reflected ray all lie in the same plane. If a reflecting surface is nearer than 15 meters, the echo joins up with the original sound, which makes the sound seem prolonged. This is called reverberation. Movie theaters and DJ sound booths are outfitted with spongy materials and heavy fabrics because these materials absorb sound. This helps reduce echoes and background noise, providing the best experience for listening to movies or recording music. In air, the speed of sound is about 330 meters per second at 0 degrees Celsius. The speed of sound increases at higher temperatures. Sound travels faster in solids. For example, in steel, the speed of sound is 6,000 meters per second. In summary, an echo is a reflected sound wave. There are 2 laws of reflection. Sound travels faster in solids, and sound travels at approximately 330 meters per second in air at 0 degrees Celsius. Comprehension. What is an echo? Where are you most likely to hear echoes? And what are the 2 laws of reflection? An echo is a reflection of a sound wave off of a hard surface like a wall or a mountain. You are most likely to hear echoes in caves, halls, or domes, or any large empty space with hard surfaces. 2 laws of reflection state that the angle of incidence is equal to the angle of reflection, and that the incident ray, normal, and the reflected ray all lie in the same plane. Comprehension. In which situation is sound most likely to travel faster? Hot air or steel? Sound travels faster in steel than in hot air because the particles in steel are much closer than the particles in hot air. Comprehension. Determine the answers for A, B, and C. Correct. A is the incident ray, B is the normal, and C is the reflected ray. For you to determine which ray is incident and which ray is reflected, look at the arrowheads. If the arrow is going towards the shiny object or towards the hard surface, then it is the incident ray. If the ray is leaving or bouncing off of the shiny object or hard surface, then it is the reflected ray. Comprehension. If D is equal to 40 degrees, then E is equal to blank. Correct. E is equal to 40 degrees as well. Because remember, the first law of reflection states that the angle of incidence, D, will be equal to the angle of reflection, E. Noise versus musical notes. Music is sound that is organized. It has a beat, melody, and rhythm. It's made to be enjoyed and can make us feel emotions. While noise is sound that is random and messy, it doesn't have a clear pattern and can be annoying or distracting. The difference between noise and music lies in their structure, purpose, and how our brains perceive them. Noise versus musical notes. Structure. Music has an organized structure, patterns of rhythm, melody, and harmony. It often follows specific scales or keys, and it is intentionally composed, while noise is disorganized sound. It typically has no predictable pattern or structure and can be random or chaotic. Purpose. Music is generally perceived as pleasant, meaningful, or emotionally engaging. Noise is often perceived as unpleasant, irritating, or distracting. Perception. Music is created for artistic, emotional, or cultural expression. It aims to communicate or evoke a feeling, while noise is usually a byproduct of activity, example, traffic, construction, machinery, and is not created for enjoyment or expression. Sometimes, what sounds like noise to one person might be music to someone else. Musical notes. Musical notes are made up of three properties: pitch, loudness, and quality. The pitch of a note depends on the frequency of the source of sound. A high-pitched note has a high frequency and a short wavelength, while a low-pitched note has a low frequency and a long wavelength. The frequency of middle C is 262 vibrations per second, or 262 Hz, and that of upper C is 524 Hz. Notes are an octave apart if the frequency of one is twice that of the other. Loudness. A note sounds louder when more sound energy reaches our ears each second. This happens when the instrument or device is vibrating with a larger amplitude, which means the vibrations are bigger or stronger. Bigger vibrations equal more energy equals louder sound. Quality. The quality of a sound depends on its timbre. It is what makes one sound different from another, even if they have the same pitch and loudness. Timbre depends on overtones, the mix of overtones above the main note. Sound wave shape, the way the sound wave looks, smooth, spiky, etc., and how the sound is made, like plucking a string versus blowing into a flute. A piano and a guitar can play the same note, but they sound different because their timbres are not the same. The difference in sound arises because no instruments except a tuning fork and a signal generator emits a pure note, meaning of one frequency. Notes consist of a main or fundamental frequency mixed with others called overtones, which are usually weaker and have frequencies that are multiples of the fundamental frequency. For example, overtones of 262 Hz are 524 Hz, 786 Hz, where 262 Hz times 2 is equal to 524 Hz, and 262 Hz times 3 is equal to 786 Hz, and so on. An oscilloscope is a special electronic tool that shows what sound waves look like. It displays sound as a wave on a screen. You can see how high and how fast the waves are, and it helps scientists and engineers study sounds and vibrations. Think of it like a machine that lets you see sound. The waveform of a note played near a microphone connected to an oscilloscope can be displayed on the screen. Notes produced by different devices can have the same frequency but will have different quality. In summary, music is organized sound while noise is random and messy. Musical notes are made up of three properties: pitch, loudness, and quality. Pitch refers to frequency, loudness refers to amplitude, and quality refers to timbre of sound. And an oscilloscope is a special electronic tool that shows what sound waves look like. Comprehension. What is the difference between music and noise? List the three properties of music. Explain what each property of music is dependent on. And what device can be used to see sound waves in the form of transverse waves? Answers. Music is organized sound because it follows patterns in pitch, timbre, and structure, while noise is random and chaotic. The main distinction is intent and perception. What is music to some may be noise to others. You never know. And the three properties of music are pitch, loudness, and quality. Pitch depends on frequency, loudness depends on amplitude, and quality depends on timbre. And an oscilloscope can be used to see sound waves in the form of transverse waves. The ear. The ear helps us hear by turning sound waves into signals the brain can understand. Parts of the ear. The outer ear catches the sound. The outer ear, the patch you can see, collects sound waves from the ear. These waves travel down the ear canal to the eardrum. The middle ear makes the sound stronger. The sound waves hit the eardrum, making it vibrate. These vibrations are passed to three tiny bones called the hammer, the anvil, and the stirrup. These bones amplify or make the vibrations stronger. The inner ear turns sound into signals. The vibrations reach the cochlea, a spiral-shaped organ filled with fluid. It also looks like a snail. Inside the cochlea are tiny hair cells that move with the vibrations. These hair cells turn the movement into electrical signals. The brain understands the sound. The electrical signals travel through the auditory nerve to the brain. The brain figures out what the sound is, like music, a voice, or a barking dog. The semicircular canals do not detect sound. They help you maintain balance and orientation. They are filled with fluid and lined with tiny hair cells. When you move your head, the fluid shifts and bends the hair cells. This sends signals to your brain about the direction and speed of your movement. That's how your body knows whether you're spinning, leaning, or standing still. In summary, the ear helps us hear by turning sound waves into signals the brain can understand. The ear is composed of three parts: the outer, middle, and inner ear. Sound waves enter the ear, make the eardrum vibrate, move the ossicles, and then reach the cochlea. There, the vibrations are changed into electrical signals by the auditory nerve and sent to the brain to understand. And the semicircular canals are responsible for balance. Comprehension. Which part of the ear makes the sound louder? And what is the name of the snail-like structure in the ear? The middle ear amplifies the sound, and the snail-like structure is the cochlea. In comprehension. How is the brain able to interpret the sound wave? And if the speed of sound is 340 meters per second, what is the wavelength of a note of frequency 340 hertz? Use speed of wave is equal to frequency times wavelength here. Please note that an approximation for the speed of sound ranges between 330 to about 350. So sometimes you won't see 330, you would see 340 or 350 meters per second. The brain is able to interpret sound waves via the auditory nerve. If the speed of sound is 340 meters per second, what is the wavelength of a note of frequency hertz? So therefore we're looking for wavelength, and we can use our triangles given. So each triangle highlights what you would have to do if you were looking for the highlighted section. So for instance, if you're looking for V, you would multiply frequency by wavelength. If you're looking for frequency, you would divide speed of wave by its wavelength. And if you're looking for wavelength, you would divide speed of wave by its frequency. And because we are looking for the wavelength, we are going to use the last triangle, where we divide the speed of the sound wave by frequency. From that we get 340 meters per second divided by 340 per seconds, or hertz, and that gives us 1 meter. Great job if you got 1 meter. Comprehension. Label the following parts of the ear: A through H. Correct. Did you get them all correct? A is the pinna, B is the canal or ear canal, C is the eardrum, D is the hammer, E is the anvil, and F the stirrups. D, E, and F are all referred to as ossicles sometimes. G is the cochlea, which is the organ that is shaped like a snail, and H represents the auditory nerve. This ends the series on sound. Thanks for watching with Miss B. Bye.